This is the first of two lectures that most of you will be getting from me today. Some will have the questionable fortune of having three lectures from me today. Those who are in 394. So I'm going to use the much of the time for today's tutorial for an additional lecture for this course. That reflects two things. One thing is that Thursday we'll be having the student presentations. I think all of you are expecting that, right? And those presentations will be scheduled for the lecture hour. So they're taking up our lecture slot on Thursday. The second reason is that I will have guest lectures following the break, and so I'd like to make a little bit more progress in terms of what we covered prior to the break. Okay, so today's lecture, first lecture, we're going to be talking about safe subclassing and the use, if time permits, of skeletal implementations, which is a very useful technique for capturing many of the benefits of what's known as multiple inheritance. Also allows you to simulate a technique that's increasingly popular called mix-ins, which provide a way to sort of mix the functionality associated with several classes together in a model class. Okay. So you may recall that I believe, in our last lecture, spent a long weekend with Hill and the Delegation for much of it. In our last lecture, we talked about Liskov substitution principle. What is the Liskov substitution principle? Can anyone remind me?
Let Q of x be equal to approximately some instance x of type S if we have an instance y of subtype of type T, which is a subtype of S, then Q of y must hold necessarily.
Good, good.
It's not going to be on the test, is it?
I think it should be. It's
Maybe it should be.
We should know. LSP is so important. We should know their hold, right?
It is.
Yeah, but I was thinking using some more
Well,
language.
not expressed in mathematics.
There's a certain crispness to the presentation that I admire. You would do well if you were to remember it in that fashion. But at an intuitive level, what is it telling us beyond that? So that's absolutely true, and that's the essence of it. But could anyone phrase at an intuitive level? If you were to explain this to someone who's not a computer scientist, how would you explain it?
If we have a subclass, we should expect the same behavior when we call the method on its superclass.
Good, good. Except I'm gonna quibble with one aspect of that. Okay. Subclass is an important case where it should hold, but it's actually a subtype.
Oh, sorry.
And one of the reasons I'm emphasizing this is because today's lecture is actually specifically about subclassing. Subtyping holds. The subtype relationships, ladies and gentlemen, of the LSP hold even if you don't have a subclass relationship, right? So really, if you have two interfaces, interface I1 and I2, and here we have a set of methods declared here, and another set there, and this claims to be a subtype of this one. A subtype, an interface, not a full class. You can have Liskov substitution principle holding or breaking just in this situation. It doesn't have to be a subclass. Now, the key thing is that this guy here can be passed around as an instance of this guy, as if it's one of these. And we can get that if they're subclasses of each other, or if they're simply subtypes in this sort of way. So today, we're actually going to talk about some additional considerations having to do with class. Liskov substitution principle, I tried to emphasize, was all about promises. promises. If you're setting up your own FedEx and you want to be viewed as a legitimate FedEx franchise and not merely as a fraudulent FedEx franchise, what promises do you have to give? Now, there's another whole question of living up to those promises, of correctly implementing those promises. So if you promise that if someone will get you the package by 3 p.m., one day it'll be delivered by 4 p.m. that day, you can make that promise and be perfectly consistent with FedEx's promises. Man, you're doing a much tighter job than FedEx. Now, implementing that, getting the package anywhere worldwide within an hour would be a challenge. So today we're going to talk about subclassing, and I'm going to highlight for you another source of bugs that have to do with subclassing in particular. Tell me, ladies and gentlemen, when I speak about subclassing, how is that different from subtyping? Here I could have two interfaces, I2 and I1. I could say I2 is a subtype of I1. I could have a class C. It can be implemented by this.
Is this relationship only prevalent? Is this difference only noteworthy in Java? Because in C++ there's no interfaces, there's only multiple inheritance modes. Everything that is a subtype is necessarily a subclass.
No, it's not. It's certainly not just specific to Java. It's not just specific to Java. And I thought in C++ there are interfaces, but I may be off about that. But I'm pretty sure there were actually support for it. In any case, it's not just Java. It's a much broader part. So if I have subclassing going on, the essence of subtyping, as far as you need to think about it right now, essence of subtyping is that if you have I2 as a subtype of I1, you can pass an I2 around as an I1. Okay? As a subtype. Subtyping allows you to make use of polymorphism. It says that all the things you can do in an I1, you can do in an I2. And implicitly that they'll behave consistently, which is what the Liskov substitution principle is about. So subtyping, ladies and gentlemen, gives you capacity to use polymorphism in object-oriented languages. Okay? Subclassing gives you subtyping, so it actually does give you subtyping, but it gives you something more than subtyping. If I say A is a subclass of B, if I say A is a subclass of B, what is that giving me more than subtyping? So why do I say it gives subtyping? Because can I pass around an A as if it's a B? Yeah. So it does give the ability to use polymorphism. So it gives that subtyping, but it gives something more. What does it give more? Yes. It basically allows us.
It would give you B, but it would give you B and an addition of, and A itself, whatever you want to add to A.
Okay. It actually, I'll boil it down to the fact that with subtyping, that I2, it carries with it all of these promises, essentially, this contract specified by I1. Over here, we actually have, with subclassing, we actually are reusing implementation as well. So all the fields that are called up here, all the implementations of these methods, we actually have now as part of A, unless we override them, right? So we're making use of all the implementations. There's no implementation over here in the subtyping world. I2 doesn't have the implementation of I1 as part of it. There is no implementation of I1 there. In subclassing, we're actually reusing the implementation. We're reusing the data structures declared in B, the superclass. We're reusing the methods declared in B, the superclass. But then we are choosing to override some of them, to replace some of them.
So I2 as a subtype of I1 actually doesn't follow any of the constraints in the contract for I1?
No, I2 does. The constraints in the contract are about subtyping.
Yeah.
The implementation, what I'm saying is subclassing gives you that same reuse of promises. It has the same reuse of the contract, but it further allows you to inherit the implementation. And there was no implementation issue for subtyping. Subtyping was about promises. The contracts involved. Is the contract for I2 compatible with the contract for I1 so that you can pass it around?
But then if you would need to supplement the contract, then you need the implementation.
If you want to define a contract, you need something that implements that contract, like
Right.
C implements.
All I'm saying is that the subtype is technically a subclass.
No, there's no subclass. There's no reuse of implementation going on subtype. There's no implementation here at all.
Okay.
Okay. Subclassing gives you use of the implementation of a superclass. You could reuse that implementation within your subclass. So your subclass has all that implementation in it. All the fields that were declared for the superclass you have here in your subclass, except any that you wish to override for the methods, right? So you may wish to knock out a method in superclass, substitute in a different method, right? So you override the print method, you override the size method or whatever to do your own bit. Does that make sense? Yes.
Is that the only difference between subclassing and subtyping? The implementation?
The fact that you're using, so we use the word inheritance. We have inheritance of implementation. I believe we could say that that's the only difference between the two. By the way, what this does mean, and maybe this is what's confusing Brian a bit, you can't subclass per se I1 because there's no implementation there. You can subclass a class because there's an implementation and promises and a contract. The contract is sort of the public methods that are available.
So the way you're referring to
Yeah.
the implementation is the fields and the methods that belong to the class.
Yeah, the things that allow it to achieve the contract.
Yeah, so it's just like you're just saying it's an empty class.
Yeah.
When it's a subtype, if it's defined as a subtype, there is no implementation at all.
There's no implementation. All it is the promise.
To further define it as a subclass, there would need to be an implementation of it.
That's right. That's right. There needs to be an implementation. There needs to be an implementation. Subclassing is the relationship between two implementations, right? The superclass, which is one implementation, a subclass, which is implementation which reuses probably a lot of elements of the superclass, but may override some, may replace some. Okay? It's a very special type of relationship. Now, this distinction wasn't really clear to people in the early days of object-oriented programming, this distinction between the two. And you had a lot of confusion in people's minds about what it was that was distinctive about object-oriented programming, etc. And a lot of people saw the fundamental benefit of object-oriented programming being reuse of inheritance, a reuse of implementation. Inheritance. The fact that if you have a class already, you can create a subclass that extends it in chosen ways, and that allows you to reuse a lot of the code. It allows you to not have to test that subclass as much or develop extra confidence in it for the subclass because it's relying on all these pre-tested things, etc. But it turns out, ladies and gentlemen, that subtyping had its own set of issues that we have to worry about with subclassing too, because it brings subtyping. if we say A is a subclass of B, we have to worry about the Liskov substitution principle in a big way for reasons that were referred to earlier. It's actually very, very important and central in the subclassing area because we have this subtyping. We can pass an A around as a B, and if an RA is going to masquerade as a B, it has to be compatible with the promise. Its promises have to be compatible with B's promises. Subclasses promises do have to be compatible with the subclasses promises because there's a subtype relationship as well. But, ladies and gentlemen, there's some thornier issues associated with subclassing, this reuse of implementation. And I'm going to expose you to them now, okay? Okay, so I want to ask, here's two classes. We went through a bunch of exercises last time. Here's a type, say it's an interface called instrumented hash set, okay? Excuse me, I have to be careful here. Right. So suppose this is hash set, and it maintains a history property. It has an invariant add all, and get add count. And here's a class that's say a subtype of it. It's actually a class that implements it. Okay. So here we have instrumented hash set, and it has an add method, and it has an add all method, and a get add count. And it calls off, to its superclass for some of these. So let me ask this. From a strictly Liskov substitution principle perspective, I presented this poorly. I'm going to edit this as we speak. This should be hash set, and I'm going to get rid of this. I think it'll be a clearer question now. Okay. So here's our hash set, and here's our implementation of hash set. This is a class. It's creating a sub. And suppose that, oh gosh, I'm not presenting this well. Treat this as if this is a class. It does have I didn't note that, but this actually is a class as well. Okay, it has this contract associated with it. This is all you know about it. From the Java libraries, this is all you know. You don't have access to the source code. You have add and add all. And now you're creating a subclass of this. Is there a subtype relationship here? Can you pass, if you do this, can you pass around an instrumented hash set as a hash set? Would Java allow you to do that? Would Java allow you to do it? I'm not saying whether it's correct. Would it allow it? Okay, it would. That's fine. Now, would it be correct? I mean, based only on the promises here, you don't have to look at the implementation, only on the promises here, in terms of what methods are provided, add all, get, add, count, and the fact that you know that what this is doing is, it's basically providing hash set, except it's keeping track of the number of times things have been added. So each time you add something, it records that fact. If you add a whole bunch of things, it records how many of them were added. And it's keeping a running total of them. Is this a legitimate, from a Liskov substitution principle perspective, from the principle of the promises being made, is what we see on the right a legitimate subtype of what we see on the left? Yes. It is. It is. From what we talked about last time, Brian's exactly right. All this does is provide some additional information. In no way, in terms of the contract on the right in no way interferes with the behavior over here to the left. If you didn't know that this was an instrumented hash set, it wouldn't change the observed behavior at all from what you're calling over here, right? So this is a perfectly legitimate subtype from the perspective of promises being made of hash set. It's perfectly consistent with the promises being made. However, I would argue that this is risky inheritance, okay? And I want to know, why is that? Why is this risky inheritance? And I'm going to clean up this slide by correcting this so that we see a consistent thing with what I just described. So imagine that it's hash set on the left, and And on the right, it's the implementation now. So now you have to look at the implementation. Why is this risky inheritance? I would argue this inheritance could be broken. I would argue this inheritance could be introducing a bug. Could be introducing a bug now, or it could be introducing a bug in the future, and you don't know whether it will come about, and it's not under your control about whether it will come about. It doesn't depend on anything you can control. Why do I say this is risky? So initially, we have add count being 0. Fair enough. We start with either no entries or some initial set, and we're not counting the number of those. We're just going to be counting up the number that we add, and similarly for this construction. So the first 3 are constructors. You don't have to worry about them at all. It's really the last 3 that you have to think about. Add all, and get add count. So what does add do? What is add doing here? Can anyone describe to me the functionality that's being captured here?
An object.
Okay. Yeah.
Increasing the amount
That have been added, and then doing
the object to the superclass.
Okay. And what does this mean? It's doing super.add, so it's calling what on the superclass? It's calling add. Yep. Okay, how about add all? What is it doing? Taking in a set of things. What's this next line? What's the first line?
Yeah.
Okay, that's good. That's a good objection. Let's suppose that we know C is non-null. Suppose there was a sort of a comment here that it's non-null.
When we add all, we take the number of things we actually have.
Okay, it depends something about the semantics of how this works, about whether we should be treating, in terms of our add count, things that are duplicates. Suppose we do want to count duplicates, so that's not so much an issue. Could this code go wrong in another way? Yes?
By using the super methods, you're basically asking the superclass to be bound to the subclass. You're making assumptions about how the superclass is supposed to work. Whereas you kind of want to go downwards, not back up.
Aha. You've actually put your finger on exactly the issue. And I'm wondering if anyone else sees it. Okay, so let's do mechanically. It does have to do with this add all issue. Remind me your name? Dustin. So Dustin pointed out that there's an upwards flow of control here. This is what's sometimes called the yo-yo problem associated with object-oriented programming. So let's go mechanically through add all work. So add all takes a collection and as a reference to a collection instance as an argument, and then it adds to the add count the size of that collection. Fair enough. And as Alex pointed out, it isn't really specified what if C is null, is that allowed? It's one of the good reasons you want to put a specification here. Put a comment saying it's allowed to be null or not allowed to be null. But we'll put that aside. So we add to the add count, and then we call super.addall. Now what does this call do? Whose add all is it calling? Calling add all where? Over here. It's calling this add all. Okay. And now add all, what do you expect it to be doing? Okay. So if it calls add multiple times, whose add is it calling? If it calls add inside add all, who?
It's calling the superclass.
No, it's calling our.
Calling our.
Which is okay. That's very good.
We said explicitly super.addall, so it's calling the addall here. But this guy, when it calls add, it's calling the most specific add, which is this one. This is why it's called the yo-yo problem, because we have this call down here for add all in the subclass, add all, and it calls add all up here in the superclass. But that add all up here, when it calls add, it may be calling to the add down here. So it goes bump, bouncing up and down like a yo-yo. Just like a piece of chalk. So, ladies and gentlemen, we have an issue. If add all does call add, what have we done? What's the mistake? Double counted. Because we counted them coming in here when we called add all. We added in the total size of the collection. And now, for each add it's calling in our class, we're adding it again. So we've double counted it. Now, if add all does not call add, just suppose it stores it directly in its data structure rather than calling add, then there's no problem, right? Our code will work properly. Ladies and gentlemen, do you control hashset? Do you exercise control over hashset? Do you exercise control over what Oracle adds into it, how it optimizes the data structures in hashset, optimizes the functionality as to whether add all calls things internally or not? Do you control that? No. Somebody else controls that. And now you are vulnerable. Even if this class works on the right, up front, it could break any time if you're using a new implementation of hashset.
So, you said that it would call the subclasses add.
Yeah.
So it would have to be defined to call the subclasses add within add.
So if the specification for add all says no, it calls a sub, any sub, this calls add internally. If that's what it said in the specification, then we can count on that. But it doesn't really say that, and so we don't really know, is it going to call add or is it not going to call add?
It's just that it may call our add.
It may call, and this is one of the dangers that comes along with inheritance. We've overridden add, and any functionality in the superclass that calls add is now calling our add. So if internally it's calling add to do a bunch of things, now we have to take responsibility for that. And in this case, our count of the number of things that are added in gets thrown off. Does that make sense as to why this is a bug? Does it make sense for why you don't know up front whether this is a bug or not when you build this class? Should you have add count here added in add all, or should you only have it added in add? Well, that depends. It depends how the superclass happens to be structured in a way that's undocumented, in a way that could change. So you could find your code, which perfectly works in one release of the Java standard library, it breaks in the next. So, here we have a client class. Maybe it's calling foo, and it's dealing with a B, a subclass. And here we call foo. There's no foo defined in the class B, so we're calling the foo in the class A. There's no more specific version of foo. So we're calling foo up here. This calls bar. When we say this dot bar, whose bar is it going to call? If this is the subclass and this is the superclass, whose bar is it going to call? Whose bar will this? So here we have a B, we call foo on it, we get this one. Now this is going to call bar. Whose bar is it going to call? Is it this one or this one? The second one, this guy here. And that's the issue, because this class may have been designed without any particular thinking that this may be overridden, right? So fundamentally, we don't know if this is correct or not. It all depends on something we can't directly observe, something over here in hash set that we don't have even the code for.
Is it possible in Java to supply a type followed by a method name that would say this?
That's a good question. Right. You could say call my one. I believe it is possible to do that. Although I'd have to go back and double check. I think it is possible, and it does something similar to super dot whatever. I think super may be a sort of specific implementation of that, but I'd have to double check that. Okay, so because subclassing involves subtyping, we first have to be careful about whatever promises we make. That problem doesn't go away. But now we have an entirely additional set of issues. We may have to be very careful about what we subclass or how we subclass, or may deviate from our promises. So when we create a subclass, we may find that we break our promises, that we don't adhere to them. We break the behavior of superclass methods, and we inherit it because we're sort of very, very selectively going around and overriding some methods and not others. And as a result, we may be breaking how the superclass works. We may be breaking how our own class work, our intended class, in a way that makes it dependent on the evolution of the superclass. So, often we'll be depending on things about the superclass. We don't know what they are. What calls what variables are updated or read by what methods. So, ladies and gentlemen, and we'll go through several alternatives for dealing with this. The safest way to subclass is to not subclass. To not create a subclass. To have a class where you prevent subclass. You don't worry about these issues. So if you haven't designed a class for a subclass, if you haven't thought about the issues that come in with subclassing, for example, helping people to understand what calls what, or what methods need to be overridden together to save functionality, you should make it impossible to subclass, for now at least. And you can do this by declaring the class as final, for example. Or you can use wrapper classes in composition, which is something we'll see either later this lecture or the lecture this afternoon. Fundamentally, though, if you have to subclass, if you want to allow options for subclassing, which is an attraction, you're seeking a way of achieving modularity in subclassing. We'd like to be able to reuse the code of the superclass without breaking it. We'd like to be able to reuse that code without being forever dependent on how that code evolves and being fragile if that code evolves in a way we didn't anticipate, the code of the superclass. We'd like to be able to adapt the set of functionality of the superclass in a clear fashion without these dependencies. And there's several ways of dealing with this, okay? Several different ways, and we'll see some of them here. One way is avoiding self-use of overridden functionality. For example, you can confine overridable functionality to just a few protected methods. Okay, and here would be something like you avoid having add-all calling add. Okay, things that are overridable, you don't call internally. Okay, so if it's overridable, you won't count on it in your own functionality directly to implement other methods. You might think that this actually lowers extensibility, but it actually preserves it. So here, for example, rather than having something like this, where we call foo and foo calls bar, and that could lead to this dependency where it ends up calling this bar, instead we have something like this. Foo will call bar internal, and we'll expose an overridable thing called bar that can be called, but that just calls bar internal as well. And so if bar is overridden by somebody, and this is the only thing which can be overridden, then it doesn't change how foo works. Foo just works just in the intended way, in the traditional way. It's not calling any different code base because we overrode bar. It allows us to change the functionality of the class as a whole. Class B can still behave differently than Class A because we have a new definition of bar, but it doesn't change internally how Class A works. Does that make sense to people, why that lowers vulnerability? Does that make sense? So in other words, you confine the overridable method to something you don't call internally. You do not call internally overridable methods. You don't count on their functionality because they can be changed by subclasses in all sorts of strange ways, ways that may not be compatible with your assumptions. So you create, if you need to call something, you call an internal method which cannot be overridden. Make sense, people? Okay, that's one way. Another issue is we can actually make use of what's called inheritance, using composition rather than inheritance. And the issue here is, let's reflect on the FedEx case. Okay. So you want to set up a FedEx franchise. Okay. Suppose you want to set up a FedEx franchise, and we talked about the Liskov substitution principle requirements for what you can promise as part of this FedEx franchise. You have to promise things that are compatible with what FedEx promises. But suppose then, as a FedEx franchise, you have a further option. You're a franchise. All you have to do is adhere to those constraints, those promises. Now, you may have the further question, okay, do you want to use FedEx's IT system or not? Do you want to use FedEx's planes, or do you want to make your own arrangements with carriers of your own choosing? If you did it from scratch, you don't have to worry about it as much, in the sense that you don't have to worry about all the details of how FedEx's systems work. You just build your own systems. You can completely spec out how you want it to work. You have complete information about how different carriers will be flying and how the IT systems. You can choose your own IT system. And you can basically build your own systems. It's a lot of work, but it's transparent as to what's going on. By contrast, you can use inheritance. And using inheritance would be like saying, okay, I'm going to opt into FedEx's system. Here we're going to use FedEx's IT system, use FedEx's planes, and all that sort of stuff. That's okay, but it comes with dependencies. You've spared yourself a lot of work, but now you're relying on implementation details of FedEx. And the key point here, folks, that I want to bring home is, if you're doing this, if you're reusing FedEx's internal IT systems and planes, do you need to know more about how FedEx works than your average FedEx customer? Yes, you certainly do. You need to know how FedEx kind of schedule things internally, right? And it's the same thing, ladies and gentlemen, with classes. If you're going to subclass another class, if A is going to subclass B, A typically needs to know more about how B works than does your average class that uses an instance of B. In other words, you're going to need to know more than is typically in the general contract associated with a class. This has a contract associated with it, B, and you're going to need to know more than that. You're going to need to know, for example, what methods call what other methods. You're going to need to know that because if foo calls bar, you're going to need to know suddenly you're going to be called internally by foo when you update bar. So you're going to be dealing with these internal calls, okay? So here, it's almost like we're inheriting and then we're customizing pieces of FedEx's systems. This goes on a lot in IT, by the way. If you go and you look at SAP, or you look at BON, or you look at other large ERP systems, enterprise resource planning systems, you buy the system and it works in a certain way, and then you tweak certain elements of it. You basically adjust certain components of it to your bidding. And you need to know how it works internally to some degree. And so it is with classes. You need to know something more about this. And there's this whole area of implementation, and I thought I had a slide on it here, implementation specification, where you're actually detailing in specifications what calls what, and if you override this method, for example, you should also override that method. You should override them together in some sort of way, in a coordinated fashion. So, for example, if you override back here, if you override add all, you should also override add as well, something along those lines. If you override the thing to read a method, you should also override the thing to write the method. If you want to store the data in a different place, you're going to have to do it both where it reads from it, and where it writes to it. Okay. So here, generally speaking, we need to know more details about the implementation of our superclass that are available to your average client. We need to know something more than is documented. So if you're going to create a subclassable class, you're going to want to provide additional information. in fact, the Java standard libraries do this by providing implementation details, for example, about what calls what. Okay. You will find in their libraries sometimes a discussion of classes that are overridable, that are subclassable. It'll say, you know, this calls this. And that's important so that when you design your subclass, you know sort of what's going on. So, in short, inheritance is very attractive. It allows you to reuse a whole lot of code. But it does so with an important responsibility. You need to understand something more about the superclass than is often present in just your average class, in just the contract for that class. If you don't have access to the superclass's code, you will want to know something about what calls what, okay? So that you could avoid breaking it in this sort of way. And then that's something that if the superclass evolves, they will adhere to that. They know that they can change a lot of things, but they can't change that because they've promised it. There's all these classes out there which are subclasses and are counting on that behavior, so they won't evolve that behavior. So if you're going to design a class for subclassing, think about documenting who calls what, and think about documenting things where there's a logical dependency between two methods. If A is overridden, then B has to be overridden as well. Okay? If you override the write, you have to override the read. Okay, let's talk about another approach, and that is the approach of delegation. And the analogy, the real-world analogy here, I said inheritance was like buying into FedEx's systems. You're depending on FedEx's planes, you're depending on their IT system. There's another approach on the software engineering side called composition, which is like a re-implementation strategy, except that you're not doing everything from scratch. It's like us using other FedEx outlets as if we're just a customer of other franchises. And here, we don't need to know anything more than the customer knows about how FedEx's works. Imagine you set up a FedEx franchise, for example, and you're adhering to all the FedEx guidelines, but you hire per layer courier. Every package that comes in, you send it to per later to deliver. Then all you're doing is you're using per later as a customer. You don't need to know all the vagaries of when their planes run and exactly how their IT system works. You've just got a customer-like perspective on it. So suppose we have this hash set, which has these sort of methods within it. And remember that we had this problem here. Here's an alternative. And this is what's called a wrapper class. You folks have probably seen these sort of things before. And it turns out there's good reason for using them. So here we have our instrumented set. And here we have our implementation for add in our instrumented set. And here's our add count. Here's our add count plus equals c plus c dot size. Here's our add count plus plus. Why does this code work? I'm going to argue this code is safe. As long as hash set is, or as long as the implementation that's passed in for set is safe, this code will work. Why is this code safe? Why is it robust, whereas this code is not? What's the difference? That's right. Well put. So suppose we call add all with a reference to some collection, right? It increments add count by the number of things in that collection, and then it calls add all on what? What is it calling on? The other code, what did it have here instead of s dot? What did that other code have? It had super dot. Here we're calling s dot. What is s? Well, s was a set that was passed in. It was some implementation of set that was given to us. Okay? It could be an empty set, for example. It could be a set with elements already on it, but it's some implementation of set. So we call add all on that set. Could that add all, by calling it, could it actually call our add? Not unless there was something really funky. Like we're passing into instrument set an instance of instrumented set or something like that, in which case actually it would still work fine. But in any case, here set, and it's just going to be calling add all, and if it calls its add, it calls its own add, not our add. So this is going to work just fine. In this add method, it doesn't override. This does not override anything. This add method is not overriding any other add. It's just an implementation of our add. Now, what's the disadvantage of this? What's the disadvantage here? It's boilerplate. Look at all this boilerplate here, right? It's very regularized boilerplate, and as such, it's easy to kind of just look at it and quickly scan it and check it. But it's a lot of extra verbiage. It won't be long before systems automate doing this, so you don't have to sort of have this all explicitly. This is what we call a wrapper class because it's instrumented set is wrapped around some implementation of set, and it's just delegating to it. It's just delegating one after the other. However, this, well, what it lacks in the way of aesthetics over here, it gains in the way of robustness compared to this. Set could evolve, the existing implementations of set could evolve in all sorts of ways. And this code will still be robust. This code is still robust. Does that make sense to people, why this is robust? People want me to spend more time on that. Okay, others?
In spite of Alex. Yeah. No, I'm just kidding.
So does anyone want me to explain in further detail why it is that add all has no risk of calling our add? This add doesn't override anything, right? This implements some interface. It doesn't extend anything. There's no inheritance going on here at all. We're not inheriting any code base, so we're not overriding anything with this add. The only way this add is going to be called is if someone calls it externally. There's no other place here that it's called. So add all here, it's going to be calling off to whatever the add all and whatever instance was passed in. And never is it going to call our add. Does that make sense? So the implementation here, it's crystal clear that here you have to add one to it, here you have to add for each of these, and you're done. Never do you have to worry that this is going to be called by somewhere else that's going to double count it or what have you. Okay? Yes? Question?
No.
Oh, yes.
I just have a quick question. If our wrapper class implements some interface, right?
Yeah.
So does our set also implement the same interface?
So the set that's passed in here does in fact implement that interface. Yeah. Yeah. So they share an interface. They're both instances that implement set, the set interface, and as such, they can both be passed around as a set. What's the nice thing here is that, ladies and gentlemen, this is much closer to what I was saying. If you want to implement your FedEx interface, the equivalent to inheritance is you have to deal with all the vagaries of FedEx's IT system and their flight times, which is a heck of a lot to worry about. That's similar to inheritance. You have to worry about the internal implementations of FedEx. They are just like you have to worry about the internal implementations of the superclass. What calls what variables are modified by what methods, so that if you override one, you can override the other in a consistent way. And that's a lot to worry about. By contrast, if you as a FedEx franchise just said, look, I'm going to take packages coming in, and I'm gonna have a contract with Purolator Courier to deliver them. I'm just a customer of Purolator. I don't have to worry anything about how they run their planes. I don't have to worry about their IT system. I'm just a customer. I just ask them to do their job. Here, ladies and gentlemen, we're not getting involved in the internal details of any type of set. We're not overriding hash set, and we don't have to worry about what calls what in it. Instead, we are just a client of some set that's passed into us. We're just calling at it through the interface, just like the FedEx franchise could deal with Purolator Courier just as a client. instead of having to worry about all its implementation details. This doesn't have to worry about any implementation detail of an existing set. Yes?
So, in the last example, the reason it was risky is because we didn't actually have access to the other
Code base.
code base. So
That's one reason.
okay, that's one of the reasons. But in this new example, what gives us access that we can now say that that class implements this delegation?
Okay. So I'll answer that in two parts, okay? Part one, I want to get back to this issue of that I emphasize one vulnerability of this guy here concerned the fact that it didn't have access to you didn't have access to the code base. Why is that just one thing that it's that's a problem with it? This is a class. So suppose we had access to this code. Suppose we had access to hash set. This is I hash set. So suppose we had access to it. Why is that still a problem? Why does the problem not go away? Suppose you're working inside Oracle. The perfect access to hash set. You know whether or not it calls add, add all calls add, or whether it just does the work itself. Why does the problem not go away? It can change. That's the biggest reason. Maybe you know it now. Maybe you go peek at the code and say, oh, add all calls add. So I don't need this. I don't need this to add it up by C size because we'll be taking care of an add. I can look at it now, but maybe it will change in future versions of the Java standard library. It could change in ways that aren't guaranteed. That's part of the whole point. I mean, if you don't provide a if you're going to have a class that can be subclassed, you want to provide guarantees people can count on about what calls what. Here, if you can't have confidence about what will stay guaranteed as the class evolves, even as its implementation internally evolves. Look at the code now, it's just going to tell you about the snapshot now. Maybe it'll be different later. So you've left this vulnerability going forward. That's a big issue. A second issue is that it's a terrible world if every time you want to subclass something, you have to go look at its code. That links us in dependencies. In terms of cognitive overhead, it's really distracting to have to go look at all these different code bases. So those are two reasons that I would argue, even with access to the code base, two testable reasons, that even with access to the code base, this problem remains. But I think there was a second important part to the question, which is what gives confidence here, as I understood it, that for example, this is a set, and this thing passed into us is a set. What gives confidence that those claims are valid, that this is a legitimate set? Did I understand your question? Okay, so broadly speaking, in software engineering, we have control over some code, and we have to take responsibility for that code, making sure that it's legitimate code. If someone passes into us a set, something that's a set here, typically we take it as base value that that's going to be a legitimate set. Okay? There are cases where there's exceptions, and we saw one earlier, for example, security risks. If they pass in a date, is it a real date, or is this a fraudulent date that's trying to take advantage of security risks? So there are cases where you sometimes look with a gimlet eye on things, be suspicious of them. But generally speaking, if we see a set pass in, we assume, okay, that's a legitimate implementation set, okay? So there we're going to assume that what's passed into us and what we store away is a legitimate set. And we're going to delegate to it as if it does its job as promised by the contract that's set. Okay? Now, as to whether this class implements the set, the set interface, we'd have to look at the set interface. And what does it promise? Well, it promises that we implement a set of methods that have to have a certain semantics, a certain type of behavior. Now, all these down below, where we're just forwarding, as long as this set that was passed in implements these correctly, we implement them correctly. That's all we're doing with delegating. We're just saying, okay, I get this argument for remove, I just pass it to this existing set that removes it. So as long as we're assuming, and almost without exception we do, that this set is legitimate, we can just use this code. This code will be correct. The question is, are these pieces of code correct? And one of the first things I ask is whether these break the Liskov substitution principle. And the answer is they do not. This is perfectly, they observe the Liskov substitution principle with respect to set. Add doesn't change the behavior, the observable behavior of how add has to behave according to set. Add all doesn't change the behavior at variance with what's promised in set. In other words, there's consistency in the promises that are kept. There's no problem at all. We provide an additional method beyond what's provided by set to provide some additional information, but that's perfectly legitimate under the Liskov substitution principle. Remember dual counter, which provided an additional counter beyond the one that we know about through a single counter, and it was legitimate. As long as you didn't swap values or what have you, it was perfectly legitimate. So we can maintain extra information, like an add count, and still be consistent with, in a Liskov substitution principle sense, with the behavior of set. Does that make sense to people? That this class could be consistent from a Liskov substitution principle perspective. Are the promises made by this class consistent with those of set? All it does is provide these methods. It provides these methods which have implicit guarantees associated with them, and the only new thing is get add count. Is this a legitimate subtype of set? Are the promises here consistent with those of set? Yes or no? Yeah. Sorry? Yeah, that's right. As long as this is legitimate, typically we assume this thing passed into us is legitimate. It is legitimate. It's a legitimate set. So as long as that thing we're forwarding to is fine, we're fine. So that's someone else's responsibility. It's not our responsibility, whoever passes it to us. This is the code we can control. This is the code we have to take responsibility. Does that make sense? So does that help at all? Okay. Yes?
I have a question. So for this forwarded methods, if we don't specify that as it and call implemented sets, does it actually call those methods?
Okay. So if we didn't specify this, so that's a great question. So if we didn't specify these methods, what would happen? Okay, so maybe, but give me more specifics about what you mean by not doing anything. What would happen if we didn't give these methods? Okay, so what would block you? What would get in the way? What problem would you encounter if you didn't define these methods immediately? What would be the earliest problem you encounter? So suppose you forgot these methods. It's a great question. Suppose you forget these methods. You forget to define them. What would happen almost immediately that would alert you to the fact that you've made a mistake?
Would tell you that it's not an actual.
Yeah, it's not a subnet because it's going to say you haven't defined a method that's required by set. The set interface requires these methods. It's going to say, go figure. You haven't defined these methods. You have to define it for set. So I'm not going to compile your code. Go up and fix it. Go add these methods in. So it wouldn't even allow you to compile this with these methods. Does that make sense? These methods are required. Correct. 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 That's right. The bottom three is stuff. Yeah. Okay, so this is delegation. Is it pretty? No, it ain't. correct. It's robust. And it prevents bugs in a way that this approach doesn't. Okay, I'd like to talk about right. So I'm going to continue on a discussion of this. So to exploit these sort of with wrappers, we need a common supertype or excuse me, a common. This is a common supertype. So so here, if we implement set, for example, we've implemented this interface. Alternatively, we could have a we could subclass the wrapper class actually from the delegate class, and we could actually end up. So that's right. So the wrapper class here, we could actually simply delegate. And do I have an example of this? Well, it'll be coming up with skeletal implementations. But we could actually have a situation where I'll come back to that issue. Okay, so I'd like to talk about skeletal implementations of something that provides the advantages of inheritance without loss of flexibility. And they use interfaces, okay? The idea here is, and you'll see this in the Java standard library, for each interface you provide an abstract class that implements the interface and it leaves certain primitive methods unspecified, okay? These are to be overridden by subclasses. And it defines many non-primitive methods. So the convention here is you have abstract and then some interfacing, abstract set or what have you, abstract collection, abstract iterable, what have you. And then people want to use the interface will then implement the interface, and then they'll commonly use a skeletal implementation or either inherit from it or create a wrapper class that delegates calls to it. So we're going to see an example of that here. So this is an example, again, from Effective Java by Block, which is a great book for those of you interested in pursuing really high-quality Java programming. So here's an example skeletal implementation. Here we have two primitives that are defined as abstract methods. What does that mean when they're abstract methods? Who can tell me? Yeah, deferred to a subclass. So here we filled in a bunch of the methods here, but we deferred the implementation of these guys to a subclass. Okay, now we could then create, you'll notice incidentally that this guy here is declared as an abstract class, reflecting the fact that that's incomplete. And here we actually see a slightly different example. So here we have a method that is going to create an abstract list. It's kind of like this. This is abstract map entry. We've left unspecified those two methods. This creates abstract list. What is this code doing? Anyone tell me? First time you see it, you may think it looks very odd. That does what? What are these guys here? What are these methods here? Good. Right. So these are the abstract methods that it's filling in. It's an anonymous class. It's a class that doesn't have a name. And it's just filling in these methods here. Okay? We're returning this. So we're returning a list where we've filled in these methods to obtain the desired functionality. We've basically just filled in a few key methods and we've reused a lot of the other functionality. Okay. If we have a situation like that, one way to use that is to create if you have a class that you want to implement safely, we can create an X list, for example, that extends abstract list, and we can fill in each of these missing elements here. But more typically, or more powerfully, what we'll do is this. So we'll have a class, perhaps we wanted to extend a different class, and it implements list. And internally, we'll have a list delegate, okay? And this will be used to delegate the various calls required to implement lists. So we'll create a list delegate by filling in those additional methods. This is an anonymous inner class. And now, whenever we get calls in this class for methods that are defined in lists, such as the size method, we'll simply delegate that to our appropriate delegate object. Okay? So, in short, here, this is like the delegation scheme we saw earlier, like this delegation scheme, in the sense that it's very robust. We don't have to worry about overriding it. And the additional advantages, we get something like multiple inheritance. Why do I say we have something like multiple inheritance? Why is this much like multiple inheritance? If there were multiple inheritance allowed in Java, where would you see it? What would it mean? Well, it would mean that you could extend two classes. You don't just have a single parent in the subclassing hierarchy, you have two parents. So here, this extends Y and it implements list. Essentially, though, we're reusing implementation of list delegate, although not in a strict subclassing way. Instead, what we're doing is we're delegating to it. So here's a class, XList, that provides all the methods of Y, provides all the methods of list. And it does so with only a very modest amount of work. It just overrides it, fills in these missing methods of abstract list. Now, the beauty of this is that if we had a full class that was this implementation of list, some implementation of list, we can't actually inherit from it directly, but we could delegate to it. And by separating the interface from the implementation of an abstract list, this allows us to be passed around as a list and get the advantages of a pretty big implementation, an abstract list, of the missing pieces. So, in short, if we just had this as a class and we filled in these additional elements, and we wanted to pass things around as an instance of this, we could only have subclasses that would superclass to us alone, because you can only superclass to one class. Here, we get the advantages, essentially, of superclassing to two classes, conceptually. We implement list with a minimal amount of extra implementation, and we implement, and we inherit from Y, too. So here we get the advantages of multiple inheritance, essentially. Any questions about this? This idea of abstract implementations of interfaces. Separating the implementation from the interface gives us the ability to get something similar to multiple inheritance. We can be passed around as a list here, even though, strictly speaking, we're not a subclass of abstract list. We can get it almost as easily. We just have to delegate to this. Okay? Okay, now let's talk about mix-ins, and then I'll finish up here. Yes. Okay. You need the time?
Yeah.
Okay. So we'll cover this later today. Thanks for the feedback.